Hello, welcome to this video, and today I want to attack a very interesting problem that comes from the British Mathematical Olympiad, Round 1, Question 1. Okay, so read this question yourself, kind of consume it. I'll go over this question, but first of all, look at it yourself. Alright, so we're given that a typist can guarantee that when they try to type a word with different letters, every letter of the word will appear exactly once. So this is a very important criteria. So we're given that the word has to contain distinct letters, different letters. And the typist will always type this word with its exact character. So he won't type any duplicates. So for example, if you have a word like math, the typist won't type M-M-A-T-H. He'll always use only these 4 letters. So that's a pretty good restriction we can put. We're also given that each letter will occur at most 1 letter late. This is pretty important. Alright, so we're also given that if we have a letter, this letter can occur at most 1 letter late, although it may occur more than 1 letter early. And this is also pretty important because it adds a little bit of flavor into the problem. So, although the letter can only at most be 1 letter late, it can always be more than 1 letter early. So, what we have, for example, for math, if we type like AMTH, this is legitimate. Why? Because M and A simply swapped, and this definitely does satisfy the criteria we're given. What about, sorry, that's the wrong color. What about HMAT? Well, H came to the first spot, but that's okay, because we are told that the letter can occur more than 1 letter early. So it can go all the way to the first. And M is 1 letter late, A is 1 letter late, and T is 1 letter late. So all of the criteria are basically satisfied. Alright, but what we want to prove is how many different spellings of Olympiads there are. Well, what we want to do, I think, in the first place, is to consider smaller letter circumstances. I.e., we want to consider how many possibilities are there for 2 letters. Let's say the letter is AB. Sorry, the word is AB. Well, if it's AB, then the only solution we have is BA. So there's 1 solution here and 1 solution here. For 3 letters, so let me just put 1 plus 1 equals to 2 total possible combinations. What about 3 letters? For 3 letters, we have ABC. Okay, so let's first, for example, give us a system of a way to compute it. Let's first fix A. So we won't change A in this position, but we can change BC. If we fix A, then the only other combination we have is ACB, where C is 1 letter early and B is 1 letter late. That's all legitimate. And I think it's very important in these kind of problems to say things out loud so you can actually hear what's happening in the question. And these are basically the only combinations we have if we fix A. But what if we put B over here? That's legitimate. That's only 1 letter early. Then A has to be in the second position. Because if A is in the second position, it is at most 1 letter late. So it's 1 letter late, and it cannot go any further. So C has to be here. What about C in the first position? It's occurring 2 letters early, which is okay. Well, that means that A can only go here, and B has to go here. So A and B are 1 letter late. We have 2 combinations over here. One combination over here, and 1 combination over here. So we have 2 plus 1 equals to 4. Let me use another color. What about 4 letters? Say the letters are A, B, C, D. Well, let's use the same problem. Let's use the same computation. Let's just fix A. Well, if we fix A, then what we have is A, B, D, C, So let's swap CD over here. Okay, that's the only combination if we fix A and B. So what we did is we basically fixed some of the letters and see how many combinations there are if we fix these letters. I think that's a very important strategy in combinatorics. So after we have A, B, D, C, we can also have, let's see, A, C as the first two fixed letters. And what we have, B has to be this letter, and D has to be this letter. Notice that we cannot switch these two around anymore because B is in the third position and B cannot go any further. Alright, what about putting AD as the fixed position? Well, that means that B has to be the third one again and C has to be the last one. B, C are one letter late, so they cannot go any further. Alright, and let's look at this. This time, we fixed A all in here. So let's fix B. Well, if B is in the first position, then what has to be in the second? Well, A, because A can only occur one letter late. So A has to be in this position. If it goes like over here, then our criteria is not satisfied. This one, remember, this is very important. So we have BA, CD. So let's just underline B so we know that we're fixing B. We have BACD and BADC. Fantastic. These are the only combinations we have because note that we are fixing B and A. At first, we're only fixing B, but after we fix B, we realized that A can only occur in this position. So what we're actually doing is fixing both of these letters. So let's look at C if it's the first position. If C is the first position, then we have A as the second position. Then B has to be in the third position because it can only occur one letter late. And D is over here. What about D as the first position? Well, that means A and B are over here. And C can only occur over here. This is one letter late. Okay, so now we have 4 combinations, 2 combinations, 1 combination, and 1 combination. And I hope you see a pattern over here. So we have 4 plus 2 plus 1 plus 1, that's equal to 8. Notice that we have 2, 4, and 8. That looks like a geometric series, i.e., that looks like we're multiplying by 2 every time. Let's see what happens if we do the next one. 5 letters. Let me just use a more vibrant color. Let's say the letter is from our previous experiences, A, B, C, D, E. Okay, so we already know our strategy right now. We're going to fix some letter, or maybe 2 letters, and then we're going to see how many combinations there are for the remaining letters. So first of all, let's fix ABC. So after fixing ABC, we have ED. These are the only possibilities if we fix ABC. What if we put AB, let's say, D over here? Then C has to occur here, and E has to occur here. And I want to point out right now that if you're clever enough, then you'll be able to realize that if we fix any letters, let's just ignore all of these. If we fix A, then we're only considering a 4-letter case. This is really important because it's going to help us produce an inductive reasoning. If we're only considering the 4-letter case, that means that if we fix A, then there's 8 combinations we have. Over here, we have 8 combinations. So that means if we fix A, we directly have 8 combinations. If we have B as the first letter, then A has to be in the second letter, remember? So we're fixing 2 letters, and there's 3 letters remaining. So we can use this 3-letter case. So in total, there's 4 combinations. What if we put C over here? Then A and B has to be the next 2 letters. And we have 2 letters here. How do we arrange these 2 letters when the other letters are fixed? Well, from here, there's 2 ways. So let's just put those two A's. What about we put D over here? Then ABC has to be over here, because they can only occur one letter late. And if they go beyond, our criteria is not satisfied. We can only have one combination over here. And last of all, what if we have E over here? Then A, B, C, D has to be over here, and that's the only combination we have. Okay, I think we already derived an inductive reasoning. Look, what we have here is 8 plus 4 plus 2 plus 1 plus 1. That's 16. And this does satisfy what I said before, that we have times 2 over here. So let's use the same inductive reasoning for 6 letters. For 6 letters, what we have is, if we fix A, then we have 5 letters remaining. For 5 letters, we have 16 possibilities. So we have 16. What about fixing B? Fixing B means we have to fix A too. So we have 8 possibilities over here. And you get the idea. If we have C over here, we have A, B fixed. And then we have 4 possibilities, and so on. So, can we derive a formula for this? Yes, of course. What we have here is 16 plus 8 plus 4 plus 2 plus 1 plus 1. And this is equal to 32. We can derive a formula now. Given a 5-letter or n-letter case, so let me just write it over here. Given an n-letter case, what we have here is 2 to the n minus 1. So if we plug in, for example, 2 letters, what we're directly given is 2 to the 2 minus 1, which is 2 to the 1, which is 2 possibilities. That does satisfy our criteria. What about 3 letters? 3 letters directly give us 2 to the 3 minus 1, which is 2 to the, 3 minus 1, which is 2 to the 2, which is 4. And so on and so on. Now, how did I actually derive this? Why am I not using rigorous proof? Well, what I want to show here is the intuition we have in order to solve these problems. We start from a 2-letter case, and we build up a 3-letter case. We realize that if we fix 1 letter, then what we have is a sub-case of smaller letter words. Okay, how many letters does Olympiad have? Olympiad has 9 letters. That means we can substitute 9 equals to n in our formula. So we have 2 to the 9 minus 1, which is equal to 2 to the 8th, which is equal to 256. This is our answer. And I think it's really important for us to realize how beautiful this is, because now what we see is all the combinations we have are simply powers of 2. And we can actually derive a very straightforward formula for this.